Okay, hi everyone, and welcome back on this part of the lecture where we're going to talk more about inodes and how the standard file systems are structured. So let's talk a bit about inodes. As we said, they don't contain the file name. That's the last thing we kind of hinted about. But they contain other things like, for example, the size of the file, as I'm listing here, or file creation times, and all the modification, access, and change times. Then the permissions of the file, we have also talked about that. And now here comes the actual part of the inode that points to the blocks that contain the data that comprise this file. Okay, so here, this is I have to say this is a historical Unix file system inode representation. I think it is valid for the ext2 file system, but again, if you venture into other file systems, like for example, I don't know, ZFS or JFS, or other types of file systems, these numbers and the actual layout might be slightly different. But it doesn't matter. In whatever file system you get to use, if you understand this type of inode layout, you will quickly figure out the equivalent on the other file system. So in the beginning, we have 12 pointers to blocks that actually are direct links. So it means like there is space for 12 blocks of worth of data. Okay, and if we said a block is for example half a kilobyte long, then this can be in total 6 kilobytes worth of data. And remember, these are not actually the blocks here, they're just the addresses of the blocks, pointers to the blocks. You can imagine by giving a block number, we can go to that block, right? So these are the links to these 12 blocks that can contain the data of the file. So if a file with a 512 kilobyte block size is smaller than 6 kilobytes in this setting, then it can fit completely in these direct links. So we wouldn't touch anything below here. But if a file is bigger, and usually they are, right? After these pointers, these 12 pointers to direct blocks, we have a single indirect. So that means this gets us to one block that this block is split to a number of other pointers to blocks. Okay, let me just show you the next slide so you get a visual representation of that. So we said here these are the first like 12 single indirect blocks, and then once we get in the first level indirect, we go to a block, and every entry on this block we can fit as many. For example, if it's 512 bytes divided by the size of the block pointer, let's say. Okay, we can fit that many more blocks over here. And then of course we have also a second level indirect, as we mentioned here, and of course a third level indirect. I don't have to go really deeper into this, but you can get the idea, and that's how we can support very, very big files. Of course, there's a trade-off here, that to get to the blocks that comprise the really, really big files, we have to go through certain levels of indirection, right? We have to go first here, then go over here, then find the relevant other block, then go over here, find the relevant block, and so on and so forth. Now, we also mentioned here that back when the original Unix file systems were being used in big servers with actual hard disks, it used to be quite an art to tune the file system and format the disk in a way that the outer tracks of the disk contain the inode information, the inode tables, and then you can go once the head starts to go towards the center of the disk, it doesn't have to turn back directly. So really good system administrators had these techniques of structuring their file systems. For example, if there was a web server that would use the /var, for example, file system pretty often, you would see the /var file system being on the outer part of the disk, while, for example, file systems that had more permanent type of storage could be on the further inside part of the disk. For example, I'm not saying this is a correct, absolutely correct metaphor, but there used to be certain file system layout recommendations. Of course, these days these don't really apply, and now modern file systems tend to keep the inode tables close to the file, the data blocks of the files that the inode tables are pointing to. So we kind of saw this picture here, and we talked about the file names. I kind of hinted on the previous video that the file names are stored in what's called the directory entry. So what is a directory entry? A directory entry, as we say here, is a sequence of pairs of file names and inodes. Okay, and you can see why when you go into a directory you see certain names of either files or other directories. And if you have noticed now from our previous lectures, like in Unix, we also have certain special names for every directory. For example, the name dot, just dot, like the dot character, conveys the meaning of the actual directory that we are in, while the double dot character, two dots, as you know, as a name, that means that we should go up one level in the hierarchy of directories. So we can to reach the inode that points to some file, we either will read the directory entry that the file is stored, as we say here. So for example, we found the file name of the file and we see the inodes that it has, or there could be links to that file, and in this case I actually mean hard links to a file. I will explain the difference between a hard and soft link in a bit, but these are there are other directory entries that might have links to the same inode. Okay, so let's take a moment before we talk about links and do a mental navigation through these data structures to get to the blocks that we want. So in here we have a traditional Unix mailbox file path, let's say. We have first the /usr directory, then we have evidently a user called AST, and then there is a file called mbox, which is probably the user's mailbox in the 90s. So let's start from the root directory. You can see the inode numbers on the left and the names of the names in the right. So what is that? This is a directory entry because it's a pair, it's a sequence of pairs of inodes and names, right? So this is a directory entry, and it is a directory entry of the root directory. So we're going to go to /usr first. So we find usr here, which is inode 6, okay, and we go to inode 6. So we go to inode 6, and then it has some metadata, and then it also has some block pointer here. It says you need to go to block 132. Okay, we go to block 132, which is another directory entry, okay, because it has a sequence of names and inode numbers, right? So then we need to find AST, that user. So we find AST, and this guy is on inode 26, okay? So we go on inode 26. Again, it has a block number here. That block number is 406. We go to that block, and guess what? We find another directory entry, but this time we find also the final name that we're looking for, mbox, and this has an inode 60. Okay, so after that, we'll go to the inode 60, which will be something like that. And in here, we'll have one or multiple blocks. And these blocks are going to actually be the data that comprise the user's mailbox. So these blocks will be filled with email, with text files that are probably emails. Also, maybe it has binary attachments, whatever, but it will be like just emails in these blocks of data. Okay, I hope you understood this little navigation here. So one question that we have here is like, do all file systems need to have inodes? Of course not, right? Inodes are traditionally in these Unix file systems, but other file systems have very similar ideas. Okay, so for example, the FAT file system, which FAT means file allocation table, okay, it has just an index table that has a certain size. Okay, so you can imagine, and there are multiple versions of the FAT file system. I need to mention here, they're like the FAT 16, different aged versions of the FAT file system, but some are very simple that you will still find just used maybe in digital cameras or very simple embedded devices, and then the FAT file system evolved to be into the NTFS file system that I mentioned below here, which is kind of the standard Windows file system that we still use, but as I said, in the traditional simple FAT file system, you had a fixed size table. It had a fixed number of entries, and the length of every file was also fixed. So it's kind of one hint in the beginning when we said, okay, what if we make a very simple file system here? It kind of has this idea. Now, the modern version, which is NTFS, it uses a B tree, which is a balanced search tree, and a balanced search tree can support, can have guaranteed lookup time, for example, or insert time that should go approximately on the big O of log n in terms of time complexity. When you do certain operations like insert or delete a node from the balanced binary tree, and it also supports like very interesting operations like having, for example, sparse files. That means if you allocate a 6 GB file but you only write 1 byte in it, do you actually need to have allocated the 6 GB? Maybe not. Or if you write just 1 byte in the beginning and then 1 more byte a few kilobytes further down, do you still need to have the 6 gigabytes allocated at any given time? No. So that is what we call a sparse file, and also it maintains instead of inode tables that we kind of talked a bit before, it maintains these MFTs, these master file tables, and the metadata lives there. Okay, and it also can support very, very big files through similar techniques like we talked about with the indirection, the first, second, and third level of indirection, the pointers, but it can support files in the exabyte range. Okay, but again, I just want you to keep from that although they're not exactly the same, the ideas translate from one file system to the next. So, seeing a bit how we can interact with inodes and find some information on inode numbers and where to look for the inodes in a traditional Unix file system. The first thing we can use is we can use a command called stat. Okay, that's going to give us a lot of information. For example, the actual size of the file, the permissions, and the inode number of the file. But also we can just use ls-i. And if you notice down here, I'm going to show it in a second. This field is actually the number of hard links. We're going to talk about in a second. So if you do ls-i, it's going to show you the inode number, but again, or stat. Now, you can watch this video that we've made that explains better the difference between soft and hard links. But just to just cover it very briefly here. The hard links actually, as we said, create a new name and it points to the same inode, while a soft link creates a completely new inode entry, okay, that points to the original file, in a sense, okay, that points to the original inode eventually. Now, the system always keeps tracks of how many hard links are currently pointing to a file, because a file is still around as long as there are hard links, any hard links, more than one, pointing to it, okay? Because someone is having, someone has a reference for that inode in that sense, okay? Once no one has a reference for that inode anymore, then that file can stop being around and the system can deallocate it somehow. And this is what I want you to see here, that I have a file. You can see this file under test_a file, and if you list it, I'm not listing with -i, so I'm not seeing which inode it is, right? But I see the standard permissions, the user, and here I see 2, because this is the number of hard links that this file has. One comes from itself, the other comes from this up here. I have made a hard link to this file, okay, and the hard link also shows 2, because it is literally the same data. It is the same inode, just it can be accessed from 2 different places in the file system, okay? While the last one is a soft link, that's why it has this L over here, and it's a completely different file. First of all, as you see, it has different permissions, right? And for example, and it only has the soft link now only has one actual hard link to it itself, right? Now, there is an open question here. What would happen if you try to create a hard link to a soft link? Think about it, try it, okay? Now, let's proceed. Let's talk a bit about solid state drives, because we have kind of hinted on how the actual hard drive looks like. But what about modern drives? We know that modern drives are actually non-memory, right? So how do they work? Well, it's a very complex topic. We're not going to go into a lot of details here, but you can imagine that these flash memory chips have certain lines, and these lines are have sequential addresses on. Now, how does it work? It applies some voltage. There is a layer of insulating oxide, so you can apply some voltage, either pointing one way or the other. When you apply voltage one way, you can take some electrons that are on the one part of the substrate and pull them up. This action happens through quantum tunneling. So these electrons are going to pass through the substrate, and they're now going to be on the top part of the substrate, let's say, and that's going to create a permanent voltage difference there that will be measured. So you can take a cell from this memory line and pull it up so that now it reads 1, like it has a certain voltage difference that we define as 1. While if we invert that voltage, then these electrons are going to tunnel back to the lower part of the substrate, and then it's not going to read 1 anymore, it's going to be 0. So that's how these NAND flash memories kinda can maintain their charge, let's say, okay? Of course, I'm sure you have heard that on SSDs there is a certain amount of times that each of these lines can be written at before they start failing. So if you have an SSD disk that you want to do a lot of writes on, then eventually this disk is probably going to fail faster than an SSD disk that you are doing mostly reads on. And therefore, also these chips, the firmware that is around these chips to drive the reads and writes to these NAND flash memories, make sure that it kind of dissipates this. It spreads these reads and writes around in a way to kind of equalize the wear and tear of these cells so that it fails in a predictable way at a predictable amount of time in the future. Okay, which you can imagine that can pose pretty interesting forensic implications, because the writes are generally spread out, and that probably means there will be data to be extracted potentially, if you have the means to extract data from these types of memories. Okay. Now let's talk a bit about how the computer boots up and how it starts, how it finds its file systems, and it finds the operating system and loads the operating system. Okay. And we're going to talk about this because that's also very important, because when you get, let's say you get a laptop to work on for a certain case, and let's say you know nothing about forensics, you decide just turn it on, and you see it booting on Windows, right? For example, well, does that mean that the laptop has only Windows and that's it? We just need to analyze the Windows file system that we see in front of us in the laptop? Of course, no. Like, there might be another file system that's just not selected to boot, for example, right? So we need to make sure we understand how the whole disk looks, and make sure that whatever partitions are there, we understand if and when they have been booted, or if they can be booted, and what types of partitions they are. So traditionally, the computer had this tiny operating system, let's say in the beginning, which was called the BIOS. It's still called the BIOS, and it means basic input-output system. It takes the first 512 bytes of a disk and assumes these 512 bytes contain what's called the master boot record, okay, which is again a predefined data structure that has certain layout, and the computer can parse it and continue to continue the boot loading process from that. So in the beginning, the master boot record has certain code, actually instruction code for the CPU, that helps it detect which partition is active, and then give control to the actual operating system kernel, because literally, the CPU is executing instructions under a very basic way here. We talked about the rings, that this, it has certain rings for protection. Now the CPU, imagine the beginning of when it starts booting the system, it has no protection turned on. Like everything works pretty directly, like it can access everything, and it just needs to find the kernel so that it can start implementing the creating the state for the operating system to live in. So after this MBR code, there are 4 partition entries, okay, and every partition entry has a certain number in the beginning, and that number is called it's a magic number, because it has nothing magic to it, but it's a predefined number that the computer knows what it means. So for example, an NTFS file system has a certain number, for example 0x7, while Plan 9 file system or a Linux file system has a different number. So one thing is this number that tells the BIOS what type of file system is there, for if that file system is bootable afterwards, okay, and the starting and ending cylinder and sector of that partition, okay. Again, let's talk a bit more about magic numbers, because we see them in forensics a lot. As I said here, they're just agreed upon constants, okay. The NTFS partition type is indeed 0x7. Now, if you change these magic numbers to different values, then the computer will get greatly confused. So that's also something to consider here. Like if you want to make a file system not bootable, maybe all you need to do is just change a magic number, right? And then the program will fail to accept it, right? Because it will say this is not a valid NTFS partition for me. Magic numbers are all around in modern computing stacks. So for example, a JPEG image has also a magic number in the beginning of the file that lets the rest of the, all the JPEG parsers and the programs that display images for you or work with images, it lets these programs quickly know that indeed this is probably a valid JPEG image, and this is the magic number for a JPEG image. Now if you change this magic number to this, for example, which this is the magic number for a compiled java.class file, then your image loader is going to completely refuse to load that file, although the rest of the data might still be a valid JPEG image, right? But because you change the magic number, the program almost certainly will not work. However, if you try to load now this JPEG image as a Java class file, like load on the Java virtual machine, it will initially be very happy to parse it, and then it's going to fail because it will not be a Java class file. Okay, you can check out Wikipedia for more standard file signatures. So here is a great visual representation of the master boot record by this guy, Jared Atkinson here. I think they have some other fantastic visualizations too. So what we see here is in the beginning we have the boot code. As we said, these are actually CPU instructions that are read and let the CPU know how to proceed to boot the kernel. And then over here there are the 4 partitions that we kind of talked about, and we see this starts with 0, 0, 20, and here it has a nice explanation of every byte we see. So 0, 0 would mean that this is not bootable, okay? Then the starting head and sector and cylinder, right? 20, 21, 0, 0. We see that 20, 21, 0, 0 here. Okay, and this again, observe that these are not in blocks. The block is the measure for the file system. Here we haven't really gone to the file system level, so things are still addressed by cylinders, sectors, and heads, like literally by the geometry of the hard disk. And if you're wondering how does it know what is the size of the hard disk, in here if you see like these disk parameters that are in this area over here, these are the parameters of how many cylinders, sectors, and heads the disk has. Okay, so it points us to where we should go and start to try to read the kernel of the operating system. And in this case, for example, it says, oh, this is an NTFS file system, okay, 0x7, you see that here, okay, and it also tells us where it ends, okay, and the total number of sectors. Now, observe something. Although this seems to be an NTFS file system, that if we trust it, that starts on 0, 0, 21, 20 here, on this cylinder sector head triple, it is marked as non-bootable, right? So theoretically, if that was an actual master boot record that we're reading, we shouldn't bother trying to boot this NTFS file system over here because it's not bootable, right? So if we're analyzing again suspect's disk and we just boot it and start looking into the file system that we actually managed to boot, we might completely miss that there is a completely different file system here that is marked non-bootable. the attacker might be able to just toggle this whenever they wanted to bootable, and then boot that file system, and we wouldn't know anything about it. Now, the second file system is marked bootable, as it's shown here, and again, it has certain parameters as we talked about. Now, the end of the master boot record is always a predefined marker 0x55, 0xAA. Okay, so if we start, reading from where we expect the master boot record to be, and we read 512 bytes, and these bytes end with 55AA, then that's a very good indication that we actually successfully read a master boot record. Okay. Now, let's talk a bit about fdisk, okay? Because we talked about the master boot record. The fdisk tool is a tool that allows us to, it shows us on a Unix machine the master boot record. Now, it allows us to see the master boot record, change the master boot record. So, for example, we could go to the master boot record and say, oh, there is a new partition for you at this offset, or delete the partition, right? Now, this just messes with the master boot record. It doesn't necessarily create a partition, fdisk. It doesn't actually. It just affects the first 512 bytes of the disk and these entries that we saw before. So, for example, here I'm listing, I have a disk SDA, the first SCSI disk on that system, and I'm listing using fdisk the master boot record. And you see, kind of, because this is evidently a privileged command, right? You need to use sudo to actually run it. Now it says, okay, this is a Samsung whatever disk, it's 500 gigs, that many bytes, that many sectors, okay? And then the units are, the sectors are, it's 512 bytes, okay? And then it has this DOS here means this is standard master boot record. We're going to see another version of it in a bit. The disk identifier, and these are the partitions that it has found here. So it has found an NTFS or extended FAT partition around 600 megabytes in the beginning, starts at this offset here, ends at this offset, that many sectors. Then another one that's like 100 gigs, again, starts here, ends here, that many sectors. And then there is an extended partition. We're going to kind of talk a bit about what an extended partition is, and then another Linux partition here, an LVM partition. So because we said that traditionally in a master boot record there is space for 4 partitions generally, we also have this idea of an extended partition, which you kind of guess it. In there, if we mark something as an extended partition, in there can be more partitions. Okay. Now, we can, when we collect using DD, as we saw in the previous set of lectures, when we collect the image of a disk and then we start analyzing it, the first thing that we would expect if we have collected the whole disk, in the beginning of that disk, we expect to find some sort of master boot record. So we can actually do fdisk-l here, as I did on my actual disk. We said everything in Unix is a file, so instead of running this on the device file, I can run it on the actual file that I did out of the computer, and then analyze the master boot record of a capture. You can go on this linked video and learn more about fdisk. Now, let's see here. I'm asking you at the bottom of the slide, how much space should I have in this disk? Okay, it says I have like 476.94, gigabytes, right? And by the way, and to point out that this Linux LVM lives in the extended partition. These are not 2 separate partitions. Here you see they have the same size. Okay. So let's try to see how much space I should have. Okay. Let's see. I have this partition, this SDA5 partition here, and it says that it has whatever that is, like 794 million, okay, bytes. Okay, is that correct? Let me verify. Yes, 794 million bytes. Now, there is a wrong comma here, please excuse me. So I have that many, actually these are like sectors, so it's times 512 bytes, okay. I have this many sectors, and that should, if you do this multiplication, it should be 406 gigabytes, okay. But so if you're doing now this sector, so you do this multiplication of that many sectors times 512, which we know is the size of the sector, as it says over here, right? If you do this multiplication, you will get 406 gigabytes. But it says 378, okay? So evidently, what's happening with that space, right? Why does it actually give me less usable size than how many sectors it reports? Well, again, we need to remember here that this file system needs to keep metadata, right? All these things I talk about, inode tables. So you can see that about 7% of that partition is not usable for me because it needs to be allocated for all this metadata, like for example the inode tables and the superblocks and all the stuff that we're going to talk about in a bit. Now, we kind of talked a bit about how to do stuff in Unix. What about Windows file systems? Well, on Windows file systems, you have this command called fsutil. You can run a parcel. You can do like you can find the parcel. You can go on cmd run and then type PowerShell and then right click and run as administrator, and then run this fsutil command. Again, you need to run it as administrator because this is a privileged command. Okay. Now this will allow you to control things like the sparse files we talked about, very complex things like storage tiers. If you have SSDs and slower disks, you can control how the storage strategy of the system will be implemented. User quotas, that means like if you have multiple users, you might want to control how much space everyone can allocate at maximum, for example, so that they don't DOS your system by allocating giant files, and the volume names and all that stuff. So you can control many parameters using the fsutil command. So I'm listing here just some sub commands of fsutil. You can always just run fsutil help and you will see all the possible parameters. But one thing here, you have like you can see through the fsinfo, you can find the drive type. Okay. Remember, we had the drive type on fdisk too. You can see the NTFS info, so that would be more like outside the scope of the things that we saw on fdisk, because that now goes into the file system. But you can, Unix also offers commands to look into the file systems. You can see how much disk is free on that volume. Okay, you can create new files. Okay, and you can also specify the size in bytes, and you can create sparse files, as we said here. You can try that, and you can also create hard links, as we used ln on Unix. You can use fsutil hard link on Windows. We're going to jump on this slide on the next lecture.